Hello students, I am Abhishek Kumar and I have been associated with the askIITians for last 4 years. I am a physics faculty here and today we will be taking up the topic of wave optics. So in today's lecture, we will deal with the wave aspects of the light. We have dealt with the rectilinear propagation of the light in our earlier classes. So let's start the class with the wave aspects of the light. Welcome guys. Today we are going to study the topic wave optics. Now in this chapter, we are going to deal with the wave nature of the light. Till now we have studied about the wave properties in general, where we have considered the wave property of the sound waves and other. Now here we will be considering the wave properties of the light. So we will be proceeding with this, and the pattern of our study will follow. Like we'll do the introduction first. So let's start the topic. Now the first thing that comes to mind is that the light is a wave. What kind of wave it is? So we know that there are two kinds of waves. One is called longitudinal waves, another is the transverse waves. Now what are longitudinal waves? Longitudinal waves are the waves in which the particles oscillate along the direction of propagation of the waves. This is the definition of longitudinal wave. Means when the particles are oscillating along the same direction that the wave is propagating, we call it a longitudinal wave. So it's like this. Suppose this is a cylindrical tube and you speak at this end. There is a person here, he speaks at this end. What will happen? A person standing here will be listening to this. So what's happening when you speak? The sound waves travel in this direction, okay, and then they reach here at this end. What is happening is that the particles in the air that you have, like here you have the particles. What happens when you speak? You apply a pressure. When I am speaking right now, the air in front of my mouth, I am applying pressure on them in a perfectly haphazard manner. Like when I am speaking, I am trying to speak sometime in a high tone, sometime in a low tone. So I am applying pressure on the air. Now this pressure is causing the air molecules to vibrate. Means when I am having a higher tone, those molecules are vibrating faster. Now this kind of disturbance that I am generating at this point, this is transmitted forward. Now this transmission, what is happening? The particles are also moving in this direction. This and this direction, moving like this, and the wave itself is also moving in the same direction. So that kind of waves are called the longitudinal waves. What are transverse waves? The transverse waves in which the direction of oscillation of particles is perpendicular to the direction of propagation of the waves. Now what happens here? If the wave is moving in this direction, the particles are moving perpendicular to this direction. Particles will be moving in this direction and the wave is moving in this direction. And they have a direction of 90 degrees between these two directions. Okay. Now these two directions that I have given you, they always have an angle difference of 90 degrees. Now this is the reason it's called transverse wave. Transverse means perpendicular. So it's perpendicular. How can you see this? It's very easy to see the situations where it happens. Suppose you have a string here. What you do is that you give a disturbance here at this point. Like I am holding this string, I am giving it the disturbance like this. What is happening is that you will find that you give a disturbance here, then you will find that after some time the whole of the string starts vibrating. So that disturbance is moving forward. You can see that disturbance is moving forward. But what is happening is that the string, you are holding the string, the particle that is at this point, this only goes like this. Obviously the whole wave is moving forward, but the particle here in the string, it is moving like this. It's not that this particle is moving like this, because if it's moving there, what it would mean that the string will break, right? So for the string to be intact, it's like it is moving like this, and the particle here is also moving like this in a different fashion from here, means in a different manner. When it is here, it may be here somewhere, something different, but all are moving in this direction and the wave is moving in this direction. So that kind of wave is called a transverse wave. Light is an example of transverse wave. Okay. Now that we have seen what a light is, what kind of properties it exhibits, we'll be now dealing with a new term called wavefront. What exactly is a wavefront? Now the wavefront is the locus of all the particles of the medium which at any instant are vibrating in the same phase. What is this phase? So before we can understand, because it's simply the locus of the points that have the same phase. So you have to find out all the points that will have the same phase, their locus will be the wavefront. So what is that phase? What is that property that we are trying to describe? So it's very easy to see. Suppose you have a wave, I denote this by A. Any wave is there, I denote this by wave. A naught times cos kx minus omega t. Okay. So this portion that you see, this angle with which it varies, this is the phase. This thing is called the phase. This whole thing is called the phase. Okay. So now if you see, this A is A naught cos kx minus omega t. So if you try to draw the figure, it will be something like this. A naught is the amplitude. What is the maximum value of this whole thing? It will always be plus 1, right? Because this is a cos. It can only go up to plus 1 and the minimum can be minus 1. So what can be the maximum value of A? So when it will be plus 1, the maximum value will be plus 1 into A naught and minimum value will be minus A naught. And then it is varying in the manner as the cos varies, right? It's simply multiplied. It's like suppose A naught is 2. So you simply multiply this variation of cos with 2. Nothing else happens. So if you try to find out the graph, it will be like this. Cos, if you remember, graph is like this. It's going like this. Okay. Now this term is the phase. What will be the phase here now? This angle, this kx minus omega t is the angle. So this is what the angle is, and this is the cos variation, right? Remember, this used to be phi. This whole thing we can write as phi. This is how the phi is varying, and then this is the cos kx minus omega. So this kx minus omega t is this axis, cos kx minus omega t is this axis. This is what it is. So A is A naught. Now this term is the phase. This whole term is the phase. Now this term could be also written like this, right? You may have cos kx minus omega t plus phi. So then this whole thing is phase. Whatever is there with this whole term, either it is cos or sine. Now this term, it could also be sine. It doesn't make a difference. What will happen is that the wave will be like this. When you will have a sine, the wave will be like this. Rest things will remain the same. This whole thing is phase. Now if this is a constant, like suppose this value of phi, you will find that in equation is simply given pi by 2 or pi by 4, anything of that matter. So that thing, it is then called phase constant because it's not changing, right? Because it is a constant, pi by 2 doesn't change with time. It's always pi by 2. It doesn't change with the distance. I am measuring here, it's pi by 2. I am measuring somewhere else, it's pi by 2. So that's a phase constant. In that case, it's called phase constant. Otherwise, this whole thing is phase. Okay, you don't have phi, doesn't matter. This is the phase. Now this angle with which it is varying, omega is the frequency. So if you are measuring the frequency, this is like this. So this is the phase. Okay. Now the locus of all the particles of the medium which at any instant are vibrating in the same phase is called a wavefront. So you have to find out the locus where all of them have the same phase. So now suppose what happens if you have a source here. This source emits electric field. Suppose it emits electric field like a charge. It emits electric field. Now the electric field that will be starting from here, when it starts from the same point, all have the same phase, right? Means this is the source. Suppose it is emitting wave in all the direction like this, right? It's emitting wave everywhere in all the directions. So now if it's emitting the wave, initially all have the same phase, right? Initially all will have the same phase. They are coming out from the same point, right? Now after some time, like suppose after a distance, a time t, what will happen? This is the point. After time t, it will be here, it will be here, it will be here. On each of the wave I am considering. Okay. Now these points that you see. Now suppose a very easy analogy I am giving you. Suppose there are 1, 2, 3, 4. There are 4 persons who are starting a race from here. All are at the same position. Okay. Initially they have the same position, means the same state. Now they all start running from here. Okay. They will all start running from here. If all of them are running with the same velocity, what will happen after any time t, they will be again at the same position, right? They start from the same position, all are moving with the same velocity, so they will always be at the same position. So now this is electric field. All the electric fields will have the same velocity because they are all identical, emitting from the same source. Everything is identical. So after some time, if this was the phase here, the phase of this and this will be same. right? Now, although I have seen here 4 only, there are infinite number, right? Infinite number of electric waves coming. So all of them have the same phase after the same time, because in the same time they have moved the same phase, they have moved the same distance, right? We are starting from here, in time t suppose reach here. Now all of this will reach the here only. All of them are originating with the same state because they are coming from the same source. So all will reach here. So all have this point. If you join all this point which have the same phase, this is the wavefront. So for a point source, it is a spherical wavefront. At a later time, you will again have a sphere like this, which will have again the same phases. Here, all the points are same phases. This is the wavefront. Now, what will happen in case of a cylinder? Suppose this is the source. So, this is after time. Suppose in time t, it moves here. So, in all the direction, it must have moved the same distance, right? So, any point that you take here, all have started from the same point, all are here, so all will have the same phase, because we are considering again after the same time. Initially they have the same phase, they all move the same distance, so again all of these points will have the same phase. So this is a cylindrical wavefront. Now this is a plane wavefront. So this point, this point, this point, all the 4 points have the same phase initially. After time t, it will have moved this distance, it will also have moved the same distance, it will also have moved the same distance, because it's the same thing, right? We are considering the same electric field, so all have moved the same distance. So if you join all this has the same phase again. Obviously the value is different, means initially suppose the value was pi by 2, after some time suppose the value is pi, but all of them have pi now. So again this is a wavefront, because all of this has the phase of pi. Here all of them then have the phase of pi by 2. So this is a wavefront. Now what is a wavelet? A wavelet is the point of disturbance due to propagation of light, means how the wave is propagating. When you have the source here, what happens? It emits light, right? Here. This is a wavefront. Now how the wave proceeds from here on in all the direction, right? At a later time the wave will be like this. How does the wave reaches here? It's like all the points that you see on this, here all the points, they all act as a source of secondary wavefront, or you can simply say a source of wave. They all act as a source of wave. So from here the wave will originate. So if this is a point source, what kind of wave it will come out? The waves will come out like this. This is a point source, again like a sphere. Like a sphere all is coming out. Okay, so what will happen when it is reaching? So if you see, all have emitted 2 waves. So if you connect these two, the top one, because then this top one has the same phase. These all points had the same phase because it was on a wavefront. Again you consider 2 circles after in all of these points. So again they will have the same phase. So this will be new wavefront. Again later on you can draw another wavefront. So these points are the wavelets and this is the wavefront. Now what is a ray? A line perpendicular to a wavefront is called a ray. Now this is the only and the most important one that we will be using to solve the questions. That the ray is always perpendicular to the wavefront. Now if you see here in this point source, the rays are actually coming, consider it as a light emitting source. The rays are coming like this. What is the shape of the wavefront? Wavefront is like this. Right? Wavefront is here at some time earlier than this, then after some time it will be here. Now this ray that you see, this ray is always perpendicular. This angle is 90 on all of this. This is 90, this is 90, this is 90. It is always perpendicular. It will never happen that it's not perpendicular. It's a universal truth that it's going to be perpendicular, and this is going to be the ray. This is the wavefront. This circular one that you see is the wavefront, which could be cylindrical, it could be plane, that we are, as we have seen earlier. But the ray is this, and the ray is always perpendicular. See here, the ray is going like this. This is perpendicular to this. How? How you can see? We know how to check whether it is perpendicular. Draw a tangent. If the angle is 90, it's perpendicular. So that's how it is happening. Here also you can see this is the light ray. It is going to here. The angle here that is being made is 90. At any point, angle is 90. Here the angle is 90. Here it's going like this. The angle is 90. So it's always perpendicular. Now if you see here, in case of a plane wavefront, which we will be normally encountering, the pink dots, these are the small pink dots. What are these? These are all the wavelets, because from here only the wave will come out. The wave will come out like this. Waves are coming out like this. And so at a later point, you can draw another wavefront. So suppose if you join all this, you will have another kind of wavefront like this. So this is how it's moving. So these all the pink points you see, these are wavelength, because from there new source will come, wavefront will move forward. This is what is happening. Now what is this blue envelope? This is the wavefront that we have seen, because what is wavefront? It's the locus of the points that have the same phase. So if initially this is what all are, this is the points that have the same phase, after some time everything will just move forward, right? Because all are moving with the same velocity. Initially you are at the same position, so after some time again you will have the same position in the same shape, right? This shape had the same phase, so again this similar shape will have the same phase, because all are moving. So that's what it is. Red line are called the rays. These are the rays, and you can see this is perpendicular. You can see this is perpendicular. It's always perpendicular. Okay. So we have seen it's the similar thing, that an arrow drawn normal to the wavefront. So you have, what you have to do is you have to draw normal to the wavefront and you will get the ray. So if this is a plane ray, this is parallel rays that are coming. So how to find out the wavefront? Draw perpendicular to it. Draw perpendicular and then join it. Draw perpendicular and then join it. So this is a wavefront. Draw perpendicular, join it. Okay. Now if you see here, if the rays are coming like this, draw perpendicular to this. Here it is this. At this point it is this. At this point it is this. Okay. So although we have shown here only 3 rays, what is happening is that there are large many number of rays, right? Practically there will be large many. So not just to make the page, keep the picture clear and so that you are able to see it, we have shown only 3. So what will happen if you try to draw all this? Again you will draw perpendicular, you will find that this kind of wavefront is being formed. Similar thing happens here. Okay. Now here the light rays are coming out. If you see, if you try to draw, this is perpendicular, this is perpendicular, this is perpendicular. So it's kind of like this. So only thing that you have to keep in mind is this, that it's normal to the wavefront. Rays are normal to the wavefront and wavefronts are normal to the rays. Both are true, both of the waves. So that's how we can solve the questions. Now see, we have a question here. Spherical waves as shown in figure strike a plane mirror. This is a wave. It's striking this plane mirror. Reflected wavefronts will be, what kind of wavefront will be this? Now you can see here, you can draw the light rays here. If you try to draw a light ray is coming like this, right? How we know that light ray is like this? Because we have drawn perpendicular to this, perpendicular to this, perpendicular to this, perpendicular to this. So it's this direction. When you join, you will get this direction. Similarly, you can have this direction. Perpendicular to this will be this, then will be this, then will be this. So join this, this will be this. So what happens to the rays after reflection? This ray will come like this ray will come like this. So this is how it is moving, right? This one which is moving like this will have movement like that. So what is happening is that now you have to draw the wavefront. So again it's easy. Now that you have the ray, draw perpendicular. Perpendicular to this will be this, perpendicular to this will be this, this will be this. So it's coming like this. It's diverging out like this. So if you try to look at the figure, this is the correct one. So if you see in this figure, you can draw the ray. What will be the ray for this wavefront? Perpendicular to this, at this point will be this, perpendicular to this will be this will be this. So if you join, this will be the ray. So you can easily see that this ray will be the reflected ray of this ray. So this is how we can solve the questions. Now see this question, you have a plane wavefront AB. It is incident on a concave mirror. This is a concave mirror, then the wavefront just after reflection is. So now if this is the wavefront, how the rays will be? Rays will be perpendicular to the wavefront. So we try to draw the rays. So rays are going like this, perpendicular to this. So that means the ray are going like this. Now it's very easy now. You know what happens to the parallel rays, right? They all pass through the focus. Suppose this is the focus. If I give, this is this, this is this, this is this. Now how to draw the wavefront? It's very easy. Now that you have the rays, draw perpendicular to this. Perpendicular to this is this, to this is this, to this is this, to this is this. So it's like this. Similarly, it will be like this, right? So what kind of wavefront can you see? This is moving in this direction now, right? After deflection, it's moving in this direction and the shape is like this. Can you see the figure anywhere? This one is the correct one. Okay, guys? So students, in today's part we saw different aspects related to the wave properties of the light. We saw what are the wavelengths, what are wavefronts, what are rays, and all those topics. Now from here after we will be dealing with the topic of Huygens principle, and we will see how we can use all of the terms and terminologies that we have studied in using these principles. Thank you.